Video, we're going to talk a little bit about utilizing the equilibrium potential, also known as the Nernst potential, to determine the direction that any ion would move under any particular circumstance. And if you see on the left here, we have the equilibrium potentials for four key ions: calcium, sodium, chloride, and potassium. Now, it's important to note that the equilibrium potential of an individual ion is the membrane potential at which that ion would have equal and opposite electrical and chemical gradients. In other words, the driving forces would cancel each other out and net movement would be zero. Now, if we come over to the right here, we can start to look at individual ions and which direction they would move given a permeability. Now, we have to start with a membrane potential starting point, and we'll use minus 70 as our resting membrane potential. Now, let's look at sodium and calcium first. And as you can see, those both have much more positive equilibrium potentials than the membrane potential when it's at minus 70. If we come over to the right, we'll remember that sodium and calcium both have inwardly directed chemical gradients. In other words, I've drawn the two ions, written the two ions where they are found in greater concentration. So they both are driven inward by their concentration gradients. Now, when the cell membrane is negative, positive ions, both of which these are, tend to be driven inward by their electrical gradients as well, because opposite charges attract. And so we could also put arrows driving them inward for their electrical gradients, which of course means that our summative gradient, the electrochemical gradient, is also inward for both of these ions. Makes it fairly simple. And so for both sodium and for calcium, both of which have a more positive equilibrium potential than our resting membrane potential down here at minus 70, those ions would both make the cell more positive, and because they're both cations, they would both move inward given a permeability. Now, let's try something a little different. What would happen if we artificially changed our membrane potential and made it positive 70? Right, so that's right about here. Right, so we've just changed our VM and artificially made it 70 millivolts. Right, so positive on the inside. That doesn't change our chemical gradients. Those are the same, and they're always the same. So our chemical gradients are still inward, but what just happened to our electrical gradients? Right, now our electrical gradients for both ions have flip-flopped, right? And so I would have to take both of these arrows and change their direction, right? Because they are now driven outward, repelled from that positive charge. So now we have to look and say, if we look at sodium, we could say, okay, well, sodium is going to drive us more negatively from that 70 millivolt membrane potential, whereas calcium would still drive us more positively. Okay, so calcium is still fairly easy, right? Because it's a positive ion. It's going to tend to make us more positive by moving into the cell. Sodium, on the other hand, is going to drive us more negatively, right? If our membrane potential is 70, meaning that the positive ion would need to now leave, sodium would now need to leave the cell to make it more negative. Right? And so the electrochemical gradient is now outward. The electrical gradient actually dominates at that point. All right, well, let's come down here to the bottom and look at chloride and potassium. Those two ions have the chemical gradients shown here, right? So chloride is driven inward by its chemical gradient. Potassium is driven outward by its chemical gradient. And if we start with our membrane potential at minus 70, we can see that a positive ion is attracted to that, so we have an electrical gradient inward for potassium, whereas the anion chloride would be driven outward by that same charge. So now we have a conundrum, right? We have gradients that are in opposite directions. We don't know which one is dominant. That is where the Nernst potential comes in, right? Because if we look at our little scale over here, both ions are going to drive us more negatively to reach their equilibrium. Which way would chloride need to move to make the cell more negative? Well, that's fairly easy, right? Because chloride's an anion, And so it would be driven inward to make the cell more negative, meaning the electrochemical gradient is inward, and the chemical gradient is actually the dominant of the two. Potassium is also going to make us more negative from a starting potential of minus 70. But in this case, it's a cation. And for a cation to make the cell more negative, it would need to leave the cell, right? Making it more negative on the inside. And so again, the chemical gradient is the dominant gradient in that scenario. So what we get at through this is that if we use the equilibrium potential, we can determine the direction that any ion will move under any circumstance, meaning when resting membrane potential is at any value.